Um, so in traditional architecture, we'll have multiple clients who are contributing and giving data. It can be our mobile phones, it can be our laptops, or it can be even from institutions like hospitals and financial institutions. So they'll be giving their data and uploading the data, and every data will be collected and it will be centrally stored at a particular database. And that database, on top of that, we will train machine learning models, and then we'll improve the model and then send it back to the clients again. So this is how traditionally machine learning architecture looks like, and traditionally machine learning works. Um, Machine learning is pretty much everywhere. It's there in all the industries and every application that we can see. One of the most important and critical application that I consider is machine learning in healthcare, and especially in medical imaging and diagnostics. Right from identifying things from PET scan, X-ray, CT, MRI, and all these things, machine learning has been really helpful for the past 10 years. And one of the recent articles that I read was, that Apollo Hospitals, a hospital that we all know familiarly, has launched an artificial intelligence tool to predict the risk of cardiovascular disease. So apart from that, even in 2020, when one of the most important, incident happened with respect to medicine field, which was the COVID-19 challenge, machine learning and its tools stepped up. And in Stanford University, they created a global AI tool to detect COVID-19 from chest scans. And you know, in medical field, this has created a revolution and encouraged people to use AI and machine learning more in medical field. Apart from that, machine learning is there in automotive industry, it's there in financial industry, it's there in manufacturing industry. Basically, machine learning is there everywhere. Um, it's also there in our everyday life, starting from the recommendation systems that we have in our favorite streaming platform, and also in Google Photos, where it's able to classify people, by identifying them or classifying even pets. So right now, I'd like everyone to, all of us to have an interactive activity kind of a thing. Um, so, you can either scan this QR code or go to menti.com and enter this particular code here. Right, if everyone is ready, I can start. Right, good to go? All right. So the first activity that we are going to do is, in your screen, you will be getting 3 boxes in which I want you to type, let's say, the letter A in the first box and the first recommendation that you get from your keyboard. And the same goes for B and the first recommendation that you get for B. And the same goes for C and the first word as the recommendation that you get for C. 1 second. Right, for some reason, not able to. Oh, right. I think can see it from here. So. All right. So from the activity that we saw, the top recommended words that we're having is "but," which is like the most popular, and almost 11 people have said that when they click B, the word that they are getting is "but," and the same goes for A as and C as call, and can is also equally competing with call. So if we go back to the so we saw that but was the most prominent word among all of us. So let's do another challenge. I hope the screen got changed in your mobile phones. All right. So how this particular activity goes up is that we are going to take but, which is the common word among all of us, and I want you guys to type but and then keep on pressing the first recommendation that you're getting from your keyboard. So, I'm getting like a lot of responses, and if you look at the responses that we are getting, it's actually, the recommendation that's getting generated, and it's kind of private to all of you people. It's sorry, it starts off, with the things that you type frequently, and also it might be certain things that are personal to you, certain things that are messages that you would type, in a private fashion, and also the passwords are also something that you type in here. So, this is how if it is going to be looking like. That is, we took the most common word that was out there, but still the answers that we are getting is, really, really different for every one of you. And it's really personal to you as well. So, if we go back to the traditional architecture that we had, so how does it work? Let's say all the things that you're typing right now is getting collected and it is getting stored in a centralized fashion. It's stored somewhere in a database. And on top of that, the model is getting trained. If that is the case, then is our data actually being safe? And what are all the measures that different organizations and softwares are taking in order to keep the data safe? For that, we have to go back slightly in time and then look at certain important milestones. So 2000s is when we had the growth of big data and machine learning, where like a lot of data flowed in, and the machine learning also took rise because of the humongous amount of data that is present. And in and around 2010s, like a lot of high-profile data breaches happened, and public became aware about privacy and how much it matters. So one of the biggest examples that I can take is the Yahoo data breach, which affected around 500 million Yahoo accounts, and it gave out their name, their email ID, their personal informations like date of birth, and even their passwords. And it became that serious that Yahoo actually asked all of their accounts, all of their users to change their passwords. And another one of the most important attack that happened in around that time was Equifax attack. Equifax was a credit scoring company. They not only leaked private information about people, it also leaked their credit transaction histories as well. So with all of this, happening in around the 2010s time, that's when in 2018, a really important policy or an act called GDPR came into play, General Data Protection Regulation. And and in that, one of the most important topic that was discussed was data protection by design. That means that whenever a particular company or whenever you are creating a software, you have to think about data protection right from the go. Like whenever you are designing itself, whenever you are prototyping itself, we have to start thinking about data protection. And that is pretty much essential. So all of these things are happening, and how does it affect machine learning? It affects machine learning even more. One, we are collecting data and then we are storing it somewhere. Two, models are also an important source of leaking data. That is, there can be model-specific privacy risks and attacks that can happen, like membership inference attack, where by looking at the model itself, we'll be able to say that whether this person is there in the model or not. And also something called as model inversion attack, where we will be able to invert the model and get the data back from the model. So since we are having machine learning models are also a really a part where it can leak certain things that are private. That's when the whole concept of privacy preserving machine learning came into play. So, and this is going to be the topic that we are going to discuss. We're going to discuss about what are all the challenges that we are going to face with respect to preserving privacy in machine learning. What are all the different implementations that's there, and yeah, that's pretty much what we are going to discuss in privacy preserving machine learning. So when I first heard about privacy preserving machine learning, the first question that came to my mind, the burning question that I had was, why can't we just anonymize data? Like say I'm giving out like a lot of data about myself. If you just strip away the fact that I am Akash out of it, then it's just some random data that we have about a lot of people, about 1 million people, right? And that's when I came across a couple of instances, and one was the 2006 Netflix price incident. So what happened is that in 2006, Netflix released their data set, all the data that they have collected about the people, by stripping away their personal information, and they announced to the public that whoever is able to beat my recommendation system, that is Netflix recommendation system, will get $1 million as the prize amount. So everything went well. The Netflix gave out their amount and everything was fine. But down the line, at one point of time, what happened is that even though Netflix has stripped away private information about people like name, email, and all, people were able to get that data set and also connect it with IMDb's data set and the current data. They were able to do a time series analysis and see that, okay, this person has watched this movie in Netflix at this point of time. The same person has, and in the similar lines, there was another person who was given an IMDb rating for in that particular time. So by matching each one of those, they were able to identify the person itself from the IMDb data. So even though Netflix tried their best to not give out information, ultimately attackers were able to identify that those people from the by correlating Netflix data and IMDb data. Another one of the most important incidents that happened was the leak of William F. Wells, medical history. So William F. Wells was a former governor in one of the U.S. State, and what happened is that he got admitted. He fainted and he got admitted in 1996. And post that, after like a lot of years, the state decided to release de-identified data for research purposes, and they removed the name, but they left behind the birthday, the sex of the person, and the zip code. So a particular person called Sweeney, tried to match different data from different sources, and she estimated that around 87% of US population were uniquely identified by birthday, gender, and zip. So you might think that birthday, gender, and zip and all these things are pretty much common. You'll not be able to identify a particular person, but surprisingly, they were able to identify 87% of US population using that. These are all examples from flat data. But if suppose you are having you're going to run deep learning on top of faces or any images, you're trying to mask it. There are enough number of digital image processing techniques and computer vision techniques to retrieve your face itself back. Even though it might not be 100% accurate, still you'll be able to get something back that you are trying so hard to mask. So what is the way out for this? So this person is called Cynthia Dwork. So she and her team, who are a group of researchers, were trying to get strong privacy guarantees while still allowing for meaningful data analysis. And this was a breakthrough with respect to the timeline of privacy preserving machine learning, where and this thing that they found was differential privacy. So what does differential privacy essentially mean? Let's say you're having a data source which consists of thousands of people's data. Let's fix your number. Let's say we are having a database which has 10,000 people's data, and we are doing some sort of analysis and computation on top of it, and then we are getting some output. Let's say I'm taking out one person out of the data set. Now the data set has 9,999 people's data in it, and we are doing analysis and computation on top of it. We are getting an output. So what differential privacy tries to guarantee is that the difference between these two outputs will only differ by a really small amount, say epsilon. So what it in turn essentially means is that even if that person is there in the data set, even if he's not there in the data set, the output is not going to change much. So if that is the case, then there is in no way that an attacker can come in and identify whether a particular person is there in the data and take out this private information. So here we have something called as difference at most epsilon. I would want to talk about it. So epsilon in differential privacy terms is called the privacy budget. And the lower the epsilon, the higher the privacy that you'll have. So basically, lower the difference that's there between the output with that person or without that person. If it is going to be low, then it means that we are having highly private, model. And the epsilon values between 0 to 1 are considered to be highly private, and the epsilon values between 2 to 10 are considered to be better than to have nothing with respect to differential privacy. So with respect to machine learning, how are we going to implement differential privacy? So one is that we are going to do two things: clipping and noise. So what does clip and noise mean? So we can limit a particular person's contribution to a model by clipping that this person can only contribute this much. Let's say in a data set, there are 10,000 records and there are 1,000 records about a particular person. Then the model will ultimately learn a lot more about that particular person than the other people. So with differential privacy, we can clip the amount of contribution that a particular person can give to a model, and also add some statistic noise on top of it, such that we are able to do computation and at the same time preserve the privacy of the people who are part of the data set. So I hope all of us know stochastic gradient descent. It's basically something that's used in most of the deep learning systems, and it is something that improves the accuracy and brings the actual value close to the expected value, and it happens over and over in iterations. We have a modified version of stochastic gradient descent, which I'm going to take as an example for explaining differential privacy, which is called as differentially private stochastic gradient descent. So how does it work? So in general, if we are going to do a process of stochastic gradient descent, then we'll take a sample of, we'll take a mini batch of training data. We'll have like millions of training data. We'll take a sample of that, and then we'll do, for example, gradients on top of it. So whatever batch that we have, whatever mini batch that we have, we'll do the SGD on top of it, and then after that we'll clip the gradients that we have got from them, and then we'll average out all of the gradients, and then we'll add noise on top of it, and this process will happen again and again. So what does this essentially mean? Let's say we are getting some data, and then we are doing we are processing it, and then we are applying the SGD on top of it, and then we are clipping it. That means that if suppose there are certain data points which are outliers in nature, that is, they are extremely different from the existing model, then these things will clip them out, which in turn might actually affect the accuracy. But still, it's important for us to find the balance between the privacy and accuracy at that point of time. So I would like to take an example which I've implemented with respect to with the help of TensorFlow. So we'll import the normal TensorFlow library, and then on top of that we have to install and import TensorFlow privacy, which is an extension of TensorFlow itself, but it does the job for privacy. And from that we'll import the DP-SDD privacy library, and this is basic pre-processing that I've done here for MNIST dataset. So MNIST dataset is it's a really common dataset. Basically, what's there in it is that in MNIST dataset you'll have handwritten numbers in a paper, and we'll have images of it, and then the model will try to predict what number it's there in that. When you give a handwritten digit, it'll try to identify the digit. So I've done some basic pre-processing here, and then these are all the parameters that we design for vanilla SDD itself, the epochs, the iterations that it goes, and the batch size that we are handling for the input. And there are 3 privacy-specific hyperparameters in differentially private SDD. One is the L2 norm clip. L2 is the Euclidean distance that is used for stochastic gradient descent. That is, you can say that it's a mathematical equation that's used to bring the actual value closer to the expected value. And this hyperparameter is used to clip that limit that potential of that particular L2 norm. So this is what I was talking about. This will clip the amount that a particular person can contribute, and also it will clip the outliers that we are having. And then we also have another hyperparameter called noise multiplier, which will add add some amount of noise that we are going to mention here. And then micro batches. So micro batches is how the data gets split into sample micro batches. It's better to have one single person per micro batch, but then it will take a lot of time for the machine learning model to compute. So we'll generally have like 4 to 5 people per micro batch, and then we'll average it out in the larger run. So we are having a simple convolutional neural network here, and so the optimizer that we are going to use for the convolutional neural network that we have is a DP-Keras STD optimizer, which TensorFlow privacy gives out of the box. And in that, we will give all of the parameters that I have mentioned. Let it be the clipping value, and the noise multiplier, and the micro batches, and the learning rate. And then on top of that, we'll train the model, and this process will go for a really good amount of time. Right. So generally, after we deploy a machine learning model or run a machine learning model, we check for accuracy. Here, it's important for us to check one more thing, which is the privacy of that particular model. So there are 2 important metrics that's used for differentially private machine learning models. One is the delta and the epsilon. Epsilon is something that we already saw, that is the privacy budget, and delta is the probability of that particular epsilon to be failed. That is, epsilon is saying that I'll keep your data secure in this particular amount. Delta says that your system can fail. Your system can fail to protect the privacy in this amount of probability. So we are having like 60,000 training points. I am giving the delta to be 10 to the power minus 5. That is the probability of which the system can fail to protect privacy, protect the data that's there inside. So with all of these, we are getting an epsilon of value 0.563, and the optimal RGP order is 18, which is basically an alpha value in the equation that is used here. This is the equation that is used for bringing the differential privacy, integrating the differential privacy with STD, and the alpha value there is what has mentioned. The TensorFlow itself does the optimization for you. It will find the best alpha value for you, such that it fits perfectly in this particular formula, and and then it gives you a epsilon value of 0.563. As we already saw, if suppose the epsilon value is between 0 to 1, then it means that the model is highly private. So we are having a model which is highly private. So this is pretty much about differential privacy. If you guys have any questions, you can take that with respect to differential privacy STD here. All right, cool. So when I finished reading differential privacy, I also had another question in my mind, which is, what if I don't trust the server? What does this question even mean? Let's take an example. Let's say I'm owning a data source and I'm making sure that the data source is completely secure and all the data that is there in that is secure. And I'm having two data points in that data source, A and B. Now I have to do some computation on top of this data source. So I'm asking some other person, and then I'm taking their server and asking them to do the computation for my data. Right. So that server is there. And I'm also trying to make sure that even during the network, when the data is going from my data source to the server, it's pretty much encrypted. Like the data is private. So I'm encrypting the data through some encryption mechanism, and I'm sending it to the server. But ultimately, when it goes to the server, it actually has to get decrypted, because encrypted value of some data is encrypted because we shouldn't identify that data itself, right? So when it goes to the server and when we have to do some computation on top of it, let's say for simple purposes, I'm taking addition to be the computation. If suppose we have to do addition of two numbers, the numbers that we had as A and B, then we can't do encrypted value of A plus encrypted value of B. We can't do addition on top of two encrypted values. But that's how it has been. And that's what I meant when I said, what if I don't trust the server? Because ultimately, at the end of the day, even if I encrypt my whole database and data source, even if I encrypt the whole network, still it has to get decrypted when it goes to the server. And the actual values should actually come out when it goes to the server. So what if I don't trust the server? How can I maneuver through such a scenario? That's when people started thinking about, can we do addition, multiplication, and basic computations on top of data which are actually encrypted. So it's almost like doing mathematical operations on top of some variables. You don't actually see the actual value, but you're expected to give the output out of it. And people said that it's impossible to do that. But then later on, Craig Gentry, who was working on his final year research project, he came up with this idea of doing addition, multiplication, and computation on encrypted values rather than actually doing it on top of actual values. And that was a turning point. And that particular thing that he figured out was homomorphic encryption. So homomorphic encryption is nothing new. It has been there for decades, and it stems from an algebra concept called homomorphism. So what does homomorphism mean? The proper definition of homomorphism is a map between two algebraic structures of the same type that preserves the operation of the structures. Okay, let's take the example that we already have. Let's say we still want to do the addition of two numbers, and then we are having A and B as our number. Let's say we are going to take a key K, which is a number that only we know, and not the server won't know about it. And we are going to do some computation where we are going to say that the encrypted value of A is equal to A plus K, and the encrypted value of B is B plus K. And whatever we are going to get as the output from the server when it does the computation should be when we do some sort of operation with respect to the key that we know, should give us back the answer which we are looking for, which is A plus B. Right. So let's say that the K is equal to 5 at this point of time, and the A and B values that we are having are 2 and 3. So right now, what we actually transmit in the network is 7 and 8. And even if an attacker comes in, he won't be able to understand anything. He won't be able to get the actual values 2 and 3 out of it. Now the 7 and 8 goes to the server. It's trying to do an addition on top of 7 and 8. The answer is something completely different from what is 2 plus 3, right? So that's where we can actually have a homomorphic function there, which is like A minus 5 plus B minus 5 plus 5. is going to be a function that's going to be there in the server, which is going to be like f of a comma b is equal to a minus 5 plus b minus 5 plus 5. So how is it related to a plus b? I have a simple graph here to show that. So this is how x minus 5 plus y minus 5 plus 5 equal to 5 looks like. And this is how x plus 5 is equal to 5 looks like. So these are two parallel lines that we are having at this point of time. And if suppose when I do minus 5, which is the key that we know, then it actually superimposes on the line that we have. That means the output that we get from x plus 5 is equal to 5, and the output that we get when we slightly shift the x-axis or the vertex of the particular graph, we get two different lines which seem different, but when we do minus of the key that we know, we get the actual values that we are expecting out of it. So this is how homomorphic encryption also works. So, if I have to say this, the 7 plus 8 or the homomorphic equivalent of 7 plus 8, we'll get something, we'll get 10 out of it. And 10 will be the output that we get there. When we do a minus 5, it'll come out as 5 again. And that is the value that we're expecting, which is 2 plus 3. So this is how homomorphic encryption, in general works. And it's just a really simple example that I have, got here, where we are actually doing this function actually has direct correlation with the key, which is 5. But then there are also complex examples, slightly complex example in mathematics itself. This is a matrix where if we have which has f of r plus s is equal to f of r plus f of s, and you have a matrix which is like this, exactly like this, then then f of r plus s is equal to f of r plus f of s, and f of r into s is equal to f of r into f of s. This is how mathematically it works. When we transfer this knowledge to encryption, then it looks like encryption of the value of r plus s is equal to encryption of value of r plus encrypted value of s. So this is what we are actually looking out for. And the same goes for the multiplication as well. Encrypted value of r into s is equal to encrypted value of r into encrypted value of s. So typically what it is saying is that two encrypted values, when they are added together, we are actually getting, we are able to compute on top of it, and we are getting the encrypted value of r plus s itself. So are there any doubts till here? Okay. There's also one more example. This is the modulus operator. This is pretty famous. If you do encrypted value of z1 into z2, multiplication of two z1s, z1 and z2, then it is equivalent to encrypted value of z1 into encrypted value of z2. But the same is not the case with respect to addition. So we have to pick and choose what type of homomorphic function that we are going to choose, and in similar way, the encryption function that follows as well. There are a few encryption functions that are pretty much famous for doing partially homomorphic encryption back in the days as well. So what is partial homomorphic encryption? So in partial homomorphic encryption, you can only do one computation. Either you can do addition or you can do multiplication. You can't do both at the same time. So one of the popular example is failure crypto system, which is used for counting e-votings. So basically, this secures the fact that you have voted to someone, but at the same time, it aggregates all the votes of people to count the votes that we have got. And this is how the failure crypto system's equation looks like. So in here, you are able to see that ultimately we are able to do encrypted value of M1 plus M2, which allows us to do addition operation on top of encrypted values. There is also another example, which I think a lot of people would have heard if you guys are interested about cryptography, which is L-gamma encryption. It is used for transferring data over the web. It's like popularly used for that, and this is how the equation for that looks like. So in here you can see that we are able to do multiplication of two encrypted values, and still we are able to compute something on top of that. And people were thinking about pushing the boundaries from partially homomorphic encryption, and that's when she came into play. So she means somewhat homomorphic encryption, and what it says is that you're able to do certain operations, but you're limited to the number of times that you can do it. That means that you can do 3 additions and 1 multiplication in the same operation. but you can't do n number of multiplications and n number of additions in the same function. So one of the examples that I have here is, let's say we are having c is equal to m plus 2 into r plus e, in which m is a binary message that we are having, and c is the encrypted value that we are trying to get out of it. Here, the encryption function that we are having is m plus 2 into r plus e, where r is a random integer and e is a really small error, which is between -1 and 1. So it's almost in decimal fractions. And if we have to decrypt this, then we'll do a modulus operator of the c by 2. So at the end of the day, we'll be able to get the value back. The 2 into r will get cancelled off, and the e that we are having is really, really small, so it doesn't really matter, so it becomes insignificant. But the problem is, if suppose we do this operation for like n number of times, then there is a chance that e, which is decimal right now, will become an actual integer at some point of time. Let's say the e value is 0.0002. But at some point, if we are doing addition and multiplication on top of it again and again, then there is a chance that it will become 1 at some point of time, and it will become 2 at some point of time. So there is a particular threshold till which we can do somewhat homomorphic encryption. But beyond that, we'll not be able to, there's a chance that we'll not be able to decrypt the value itself. So it's almost like adding too much amount of noise on the actual data that we are having, that we are not able to get the actual data itself back from it. So that's when Craig Gentry brought this concept called bootstrapping, where through mathematics and through lookup tables, he brought something similar to this, where if suppose the noise goes beyond a particular point of time, he found a mechanism which reduces the noise back to the level in which we are able to decrypt the answer from the ciphertext itself. So that created something called as fully homomorphic encryption, allowing people to do multiplication n number of times, allowing people to do addition n number of times on top of integral data. And this is how the flowchart looks like. For almost 30 years, from 1978, we were only handling with partial homomorphic encryption and somewhat homomorphic encryption. But in 2009, the first generation of fully homomorphic encryption came into play. And but the problem with that is, for even simple computation, it took almost 30 to 40 minutes for it to do simple, addition and multiplication operation, because it's computationally intense. Then the second, generation came into play, where they slightly improved the performance, but still they were having limitations with respect to what type of data and what operations they can do on top of. Only in fourth generation, we were able to do machine learning stuff, because that's when matrix multiplication, matrix addition, and decimal operations were we were able to perform on fourth generation, and that's what led homomorphic encryption to get integrated with machine learning and deep learning. So at the end, you can see something called as Zama, which is basically a leader in this particular. They specialize in releasing homomorphic encryption libraries and products and systems as well. So one of the libraries that Zama has for this is ConcreteML, which I have used here in an example. So what we are having is a health prediction system using fully homomorphic encryption. So we already saw that the health data about a particular person is really sensitive in nature. We're going to do a simulation here with the Zama, what Zama produces out of the box using the ConcreteML. So it's asking us to give the complaints that we have about us, and we can give whatever that we have about us. I'm just giving some random values at this point of time, and we can say that these are all the problems that I have. So basically, what this machine learning software is trying to do is that it's trying to identify the disease that you're having based on the symptoms. So I'm giving the symptoms here, and I have submitted the data. After submitting the data, we can generate the keys. Here it is going to be a complex key. In our example, we saw something like k, which is equal to 5, right? Similar to that, here we are going to generate some keys, and then we are going to encrypt the data on top of that particular secret key. So what actually should look like a symptoms vector here, where I've ticked a few boxes and those things have become 1 instead of 0, they will become an encrypted vector which we won't be able to identify or analyze. And then we'll send the data to the server side. So we have to run, after sending it to the server side has to do the computation or do the analysis on top of the data that we have sent and actually predict what disease this person might have. So for that, they have used logistic regression here, but the model needs to be trained on top of encrypted data for it to make sense of whatever is coming inside, right? So that is being done here, where it is, even though there has been like complex mathematics that was explained and a lot of evolution that happened, at this point of time, it is almost as simple as using your simple scikit-learn library. But if you install pip install concrete ML, and then on top of that, if you import the concrete XGB classifier, then you can use it as simple as how you are using a normal XGB classifier itself. So here you can see that. That's pretty much it. Where we have so basically that will take care of training the data on top of encrypted values. So in general, when you have a normal scikit XGB classifier, it will train on top of the actual values itself. But here, the concrete XGB classifier will take care of everything out of the box. That you can actually train it on top of encrypted values, and you can even test on top of encrypted values, and then based on that, you'll be able to the model will be able to predict whenever it gets an encrypted value. So one of the most important things that this particular library is trying to achieve is to bring down the inference time as low as possible, because this particular homomorphic encryption, when they started out, it took them around 40 minutes of time to do a simple mathematical computation, right? As I mentioned. So they are trying to bring down the inference time that this particular model takes, and we are able to see that it's coming down to 7 seconds, 27 seconds, 18 seconds, and all those things for a particular data point that's coming in. But still, in machine learning terms, it's actually taking a really good amount of time for training the data. So this is what I have with respect to homomorphic encryption and how we can use it with respect to Zama and concrete ML. Do we have any questions with respect to homomorphic encryption? Yes. Right. So one thing is that concrete XGB is trying to bring the accuracy as close as possible by having the time as the trade-off, the amount of time that it takes to do the computation. But yes, with respect to the previous topic that we had, differential privacy, as well as here, there's a significant dip in the accuracy. So it's not as accurate as the normal models, but at the same time, it's almost like the trade-off that you have between privacy and the accuracy. So the more private your model is, the lesser the accuracy will be. You have to find a sweet spot in between and go with that. Yeah. I mean, okay, differential privacy, we saw homomorphic encryption, but still there are certain problems that we are not able to address with respect to privacy preserving machine learning, right? One is that the Yahoo data breach that happened, where it was actually all of the data was stored centrally that someone was able to attack it and get private information out of it. Also, one more was the Netflix price incident, where people were able to get the actual data about people and their watch history and all those stuff. So this made me as well as Google wonder, why can't we just decentralize the data? Why can't we just have the data in the edge devices itself? We don't need to collect the data itself. Let the data be there in their own devices. We'll just send the model to the data and we'll train on top of it and we'll be perfectly all right. It's what they promised in the paper that they released in 2017. And that was an inciting incident which changed the course of privacy preserving machine learning. This was the paper that they released in 2017 called Communication Efficient Learning of Deep Networks from Decentralized Data. So what they actually promised was let the data be there in your local device itself. I'm going to take our mobile phones as an example because that's where there are highly private information, and at the same time it's easier as well. So they said that the data will be there in your mobile phones only. We will send the model from somewhere, and in your phones it will get trained, and the model will get improved, and then on top, and then the mobile phones will send the model back to the server, and every model will get aggregated so that we try to make a better model of it. So we saw the examples in the first few minutes, right? The Apollo hospitals, they are using this particular technology. The COVID-19 challenge that we saw with Stanford University, they are also using this particular technology. And if we like slightly scroll this research paper, we'll be able to see that the first two problems that Google tried to solve was one, the image classification, which they had with respect to Google Photos, and the second was the prediction, the next word prediction in the keyboards. So, which was the activity that we did. So this particular concept or technology is called machine learning on edge because the machine learning happens on the edge itself instead of happening somewhere centrally. It is also called decentralized machine learning for the same reason, but formally it is called as federated learning. So at this point of time, we'll take a short break, then we'll do a small quiz sort of thing, so that we'll be able to understand. We'll come to a common ground of an understanding that we have with respect to machine learning, which will be helpful for federated learning. So if you go to the same link itself that I shared previously, I think you'll be able to get the quiz. Or if suppose someone's left out or something like that, they can scan the QR once again. All right, let's go. Yes. Should I start the quiz? All right. All right. Good enough. So machine learning model basically maps inputs to outputs based on the patterns that it has already learned from training data. Right. We have many more. All right. So parameters in an ML model are the variables that we adjust during training time. More formally, suppose if you are involved in machine learning and deep learning, you can say that weights, biases, the gradients that we have in those can be set as the parameters. And also the parameters that I was talking about with respect to the alpha that I showed and the epochs and the privacy and all those things that we saw are parameters in ML. All right, super. So weights in an ML model are basically variables that determine feature importance. They say how important a particular feature is in predicting something, or in classifying something, or in identifying the value of a particular thing that the model is trying to predict. I think if people know what weights are, the next question is predictable. All right. Okay. So what do biases do in a model? So we know that weights are something that gives more importance to the feature. It says how important a particular feature is. But biases is what course corrects the gap that we have with respect to what we are trying to achieve. It's almost like how many of you guys know the straight line formula? It's super similar to that. Y is equal to mx plus c. Similar to that is how in like really simplistic terms weights and biases work. It is y is equal to w into x plus b. So y is the output that we are trying to predict. W is the weight, X is the feature, and W will determine the weight of that or the importance of that particular X. And B is something that is there to course correct, how course correct the actual value to the expected value. All right. Super. I think all of us agree on this. It is to improve predictions and reduce loss. So weights and biases actually play a critical role in deep learning models for us to understand and improve the predictions and reduce the loss. Oh, so parameters are updated by minimizing the loss function iteratively. This is basically what I was talking about as stochastic gradient descent. That also does almost the same job by minimizing the loss of that function iteratively. All right. So go. So they are the slopes of the loss function with respect to parameters. It's a mathematical function that helps us to bring the loss, reduce the loss as much as possible. Okay. So learning rate is something that will tell us how similar to how weights work. Learning rate will tell the gradient how much should we change. What is the importance of that particular iteration? The gradient have the loss reduces iteratively. So basically, learning rate is something that will tell how much the parameters should change per update. It is like how weights work for the x values that we have. Similar to that, learning rate works for the gradient. Oh, super. So it's done. I mean, it's pretty much almost the same thing to improve prediction accuracy by reducing the loss. So I think at this point of time, we've got to know how much important the model updates and the weights and biases are. The last question. This is something that I was expecting, and I'm happy that all of you guys answered. Model updates like weights, biases, and weights. So this is pretty much the foundation for federative learning itself. So they said that I'm not going to share the entire data set. It's not going to be available centrally. I'm not going to share the predictions that we get from the model, because through predictions that we get from the model, you'll be ultimately able to attack or identify the data set itself. I'm not going to send the pre-processed raw data. I'm going to send model updates like weights, biases, and gradients, which are something that affects the model, and at the same time, they don't reveal anything personally. So let's look at how it's done in federated learning. But before that, we'll look at the quiz report. Oh, okay, who's Nemo? Oh, nice. Good job. All right. So federated learning from a different definition perspective, is the machine learning setting where multiple entities collaborate in solving a machine learning problem under the condition of a central server or service provider. So basically, we have a server which is orchestrating all the nodes, and this is how it looks like. We have a central server, it is orchestrating all the edge devices, and we have the edge devices where the data is going to stay in the edge devices only, but it's only going to send model updates like weights, biases, and gradients to the central server, and the server will aggregate all the nodes, weights, biases, and characteristics of the model, and it will develop a new model, and that model will get deployed in the edge devices again, and this process will iteratively go on, and it improves the accuracy of the model. So in federated learning, even though the server is the orchestrator, the edge device or the client is the one who initiates the process. It's our mobile phones which will ask the server, do you need me at this point of time? And even in that, there are specific scenarios only in which the mobile phones will ask, do you need me at this point of time? It has to be in charging, and it has to be on a metered net. It has to be on an unmetered network, which is Wi-Fi, and it should be idle in nature, so that it doesn't really affect the performance of our phones, and it still contributes something to federated learning. You can actually change the federated settings which is there in your mobile, and the choice is left up to you. But federated learning is turned on by default in every Android phones. But you can go to the language and input, an on-screen keyboard, and keyboard privacy, and you can choose the level of privacy that you want, and you can choose what is the level of privacy that you want from there. So when the server says yes, I want you at this point of time, then the server sends an initial model to the edge device, and there, using the local data that we have in that edge device, the training process happens here, and after the training process, an updated model comes out in the edge device itself. So one of the the first privacy principle which federated learning follows is it only collects what is required. It doesn't collect anything beyond and above that. Like, from which device it is coming from, what is the email ID of the data, nothing goes out. It only the model is getting collected here, and even in there, it doesn't really store anything. It only stores the model. It doesn't store any metadata that is surrounding the model. So this is one device that we saw here. Like that, there will be multiple devices which will be contributing for federated learning at that point of time, and all the updated model of those edge devices will join here at this point of time in the server, and will get aggregated to give a combined new model. And this new model will be another model for another set of iteration, and this will go to the edge device, and the same process will repeat again and again. So the very first algorithm that Google proposed was federated averaging algorithm. So what happens is that in every single edge device, sets of SGD will run, and it will produce the updated model on the local data. And on top of that, the server will do just the average of all the models that we are getting. Models in the sense, let's say, for example, I can say that a matrix of weights from different people is coming in, and the server will do average of that, and then it will try to produce a new model. So this is how the federated averaging algorithm works, and this is how the algorithm looks like. So let's say we are having k clients at a particular point of time, indexed by k, 0 to k, and then we are having the server executes, and it initializes the let's say W is weight here. We are doing this iteration for weight. So it will go on iteration, and then for each client k, in parallel they do client update. Client update is basically the SGD that is running on each client device, and then we will get the weights out of it, the updated weights out of it, and that weight will get summed here. It will get summed and it will get averaged out. So that's how federated averaging works. So basically, we'll get different weights from different clients, and then the server gets all the weights, and then it averages all the weights and gives a new weight. And based on that new weight, a new model is created, and that model goes in this iteration once again, and it goes on and on. So the typical orders of magnitude that we are looking at with federated learning are 10 to thousands of clients participate per round, and around thousands of rounds it takes to converge to a really good model, and it takes 1 to 10 minutes per round. So now you get why it is done during specific scenarios like charging, Wi-Fi, and idle. It's a really computationally heavy process, but at the same time, it's making sure that it's not affecting your performance while you're using it. So TensorFlow provides federated learning APIs and APIs out of the box. So it has two APIs. One is the normal federated learning API, which allows you to implement existing algorithms like federated averaging. It also has federated core API, which lets you build your own algorithm itself, like similar to federated averaging. Apart from that, it also gives you local runtime for simulations. So in general, whenever you're using TensorFlow or any library for machine learning or deep learning, you'll have the whole data present in your system locally or somewhere. But here, the data is actually flowing in from multiple client devices. So we can't do a model training on top of local data and see how it matches up with people from different clients or different edge devices are coming in and contributing, right? So for that, they also have a local runtime simulation, local runtime, where we can actually simulate as if thousands of clients are participating and giving the data instead of it actually coming from our storage. So this is a small example that I have where each device has the temperature sensor on it, and it gives the temperature values. So how does it work in TFF? So in TFF, we have a function called federated mean. So what it does is that, it tries to do the mean from various different clients that it's getting, all the values that it's getting. Even though the clients are, n number, the clients are n number, and you're having a server which is completely different, you can still write this function as if you're writing a simple Python function. And that's what it tries to achieve. So let's say we want to crack a simple problem of identifying whether today is hot or not. So for that, the server will broadcast its own threshold. Let's say it has, 75 Fahrenheit as the threshold for saying that beyond that point of time, it's going to be hot. If it is not, then it's cold. It's what it's having. And, it is sending that data to all the edge devices. And in there, the local computation happens. Here, it's just a simple, comparison that's happening between the data that I'm having and the data that has been broadcasted to me. And you can think of it as MapReduce if you're familiar with, distributed systems. And after that, everything gets averaged out and it gets meaned, and it goes back to the server again, and this process goes on and on. So this is how a sample code looks like. So you have to mention the type for TFF to identify what types you are sending in. There we decided that the clients will send float 32 values, and the server will have will aggregate everything together. And even though this looks like a simple Python code, it's actually a TensorFlow code, and that's why you have to decorate it with the TFF federated computation and the annotations that are there on top of it for it to understand the Python code and convert it into TensorFlow code. So this is a small example. I have an actual example from machine learning, which uses the same MNIST data set for identifying the numbers out of the handwritten digits. So we have to import TensorFlow federated for this. Similar to how we imported TensorFlow privacy for differential privacy, we have to import TensorFlow federated for this. And then we have to prepare the input data. So as I said already, this is not a simple data set that you can load from somewhere or you can load from local. You have to simulate the fact that multiple clients are actually contributing to TensorFlow. So the TensorFlow itself provides a simulation environment where it is trying to load the data of MNIST. And it's saying that almost 3,383 clients are present in this simulation. And then we are processing the input. So what we get from the clients is basically a square image, which has a handwritten digit on that. So it's a 28 cross 28 image, and we are trying to flatten it into a single dimensional array. It's a two-dimensional array which has a lot of pixels in it and the values of the pixels in it. We are trying to flatten it in a one-dimensional array so that it will be easier for us to compute. So this is how it will look like an array of, it is like this when we get it, and then after that we, flatten it into a single, single dimensional array. So when we actually look in production level scale, the choosing of clients process happens based on their availability, based on whether they are connected to Wi-Fi and all those criteria that I talked about. But here it's everything is there in local. So we'll randomly have some number of clients, and we'll ask the simulation environment to give us this amount of clients. In this, for simple purposes, I have taken 10 people who are trying to participate in this federated learning experiment. And then I have defined a simple sequential model, and then here we are what we are trying to do is we are not calling the function as of yet. We have just defined it. So what happens is that in the TensorFlow, in the federated environment, that itself will choose the best time to call the particular function and initialize the model instead of us actually doing it. So after defining the model, we have here where we will actually initiate the training process. They will specify the algorithm on which we are going to do the federated learning, which is a weighted federated average. Whatever we saw was a normal average, federated average. This is the next version of it, which is weighted federated average, where we will say that this client has more importance. This particular thing that is coming from this client has more importance, and we give weights. So we are having two optimizers. One is a client optimizer and a server optimizer. Client optimizer is for the HDD that is running on each client devices that is being participated in this predictive learning. And the server optimizer is the HDD that is running on the server, on the cloud, where it is trying to rebuild the model on the averaged out weights and biases that they have got. So the most important function is initialize. When we say training process dot initialize, it starts the process of predictive learning, and then you can iteratively go through the rounds of predictive learning by doing dot next. So dot next basically takes in a train state, which is the previous state in which the process left out, and then it will give in the data that giving the data of the clients that are willing to participate at that point of time. So this is how it has happened in the round one, where we have got the metrics as well from it, saying that this is the accuracy, this is the loss that we have got, this is the number of examples that went in for this particular iteration, and these are the number of patches that we have scripted to. So we can do this process iteratively again and again, and this is what is essentially happening in production level as well. This is a simplified version of it, but this is what is happening in production level as well. And you can see that slowly as accuracy is also increasing. It started off from 0.14, it has gone to 0.32. Upon doing this for multiple times, the accuracy will improve to such a state that it is able to classify or predict things properly. All right. Are there any doubts with respect to the code? So, as I said, this is a really simple example, but Google has, took up the challenge and made it possible for us to do it in a really large scale, and that is what is happening with us in Gboard. So, where our next word predictions accuracy has improved about 24%, and people are feeling that the prediction strips that they are getting, like the 3 boxes that we'll get right, or even more when we are typing something, it has increased by 10% more clicks. There are people actually using it more after predictive learning came into the picture. So it is also used in emoji prediction, and it's also used in action prediction. Sometimes when you are doing certain stuff, Google recommends you a GIF, or it actually recommends you to do a search or something like that if you have noticed. So even that is using predictive learning, and it also helps the model to helps Gboard to get to know about new words, all the Gen Z term and slang that we are using. Gboard is able to add it to its own dictionary such that it gives us predictions for other people when we are typing it in the Gboard. Not only in Google, Apple also uses predictive learning for Siri, and it personalizes your data without even actually leaking it out anywhere. So all the examples that we saw till now is cross-device predictive learning, where there are multiple client devices like our phones and all those things that actually contribute to a server, and there's a server orchestrator, and it contributes to predictive learning. But then there is another concept called cross-sale of predictive learning, where organizations come together and they say that I'm having these huge number of data, but it's really private to me, and but still I want to improve the predictions that I'm doing. So I want to collaborate with some other organization, but I'm not ready to share my data with that organization. So in those scenarios, predictive learning has become the bridge for them to actually keep the data with themselves, but improve the model on top of it. So actual practical examples are from when Intel partnered with UPenn for cancer prediction and brain tumor classification, where multiple organizations and healthcare industries came together, and they said that I'm going to have the data with myself, but this is going to orchestrate and make a new model and a robust model that will try to classify brain tumor. Similar example from NVIDIA, where they have brought in multiple medical institutions for mammogram assessment using AI, and what's running behind it is predictive learning. Not only that, we'll go slightly out of medical situations. Even Mercedes-Benz has partnered up with NVIDIA for using predictive learning on self-driving systems with automated routing and car parking. So, what is the This says that cross-silo federated learning is really as important as cross-device federated learning. There are a few differences that I want to emphasis on. So cross-device federated learning, you'll have millions of client devices, but in cross-silo federated learning, you'll have really small amount of client devices, and these millions of client devices that we have for cross-device federated learning are not really sure whether they'll participate in every single round, but in cross-silo federated learning, they'll participate in every single round. So one more, exciting thing about cross-silo federated learning is that in cross-device federated learning, or the people are different, who are contributing are different, the edge devices are different, but what are the features or whatever they are contributing to is the same. But in cross-silo federated learning, you can actually bring two different institutions together and do, computations or predictions on top of it. As an example, I can actually we can actually collaborate medical institution and a cybercrime institution, saying that and then we can identify the correlation between how a particular person, a criminal, has how often does a criminal get health diseases, or because of certain health diseases, how often does he become a criminal, without even actually sharing these two data among themselves. So this is the whole flow of federated learning. But where all can we actually can an actor learn about private information? So basically, actor is a posh term for attacker or people who are really curious to identify personal information about other people. So there are multiple touch points. One is the device. From there, they can identify private information. From the network, from the server, from the released models and the deployed models. We'll go one by one. So with respect to the device and the network, you can always, as I already said, you can always say no to federated learning by turning it off in your mobile phones. But apart from that, by default itself, encryption happens at every stage. It happens during the transmission and it happens in the edge devices as well. But with this as well, there is a really important issue that's present. How can we make sure that the model doesn't identify a person? How can we ensure that a particular person is not contributing too much to the model, that the model is able to identify the person? We have already seen this concept, which will be used here. It is the differential privacy. So by transmission itself, at times local differential privacy is applied such that we limit the contribution of a particular person to an average value of how much everyone else is contributing to. And then we have the server. I think we already know the answer for that. I mean, it started out with the question of what if I don't trust the server? So the answer to this is homomorphic encryption that we already saw. But apart from that, there are also two other interesting concepts called secure enclaves and secure multi-party computation. Secure enclaves is more inclined towards hardware-related stuff and how it makes the data secure. But secure multi-party computation is something that I will talk about in a few slides. It can also come from the released models and metrics, right? So how do we handle that? We can actually deploy central differential privacy here after the model gets predicted. After we get the released models and metrics, we can apply differential privacy on top of that and adding some noise to the model that we have got, such that no actor is able to identify private information from it. So we first saw differential privacy, and then we saw homomorphic encryption, and then we saw federated learning. And in a few slides, we'll see a concept which is related to secure multi-party computation. So today we are in a position where we are able to say that our data is secure and the privacy preserving machine learning is the top because of the convergence of all these topics together. So we look into each one. We will look into one by one. Starting off with secure aggregation, this is the example that I was talking about, secure multi-party computation. So how does it work? So here I've taken an example of Alice, Bob, and Carol, who have generated their own local models by their local data. These are all the models that we have. And, let's say the green triangle is Alice's model, purple triangle is Bob's model, and the orange triangle is Carol's model. We can actually add an anti-particle, which is exactly the opposite of what the model has produced. Let's say it has produced a one-dimensional vector of weights. then we can actually have another, anti-particle, which is negative of that one-dimensional vector of weights. And we can distribute it across the people who are participating for federated learning. Let's say the Bob's antiparticle is with Alice, and Karen's antiparticle is with Bob, and Alice's antiparticle is with Karen. So, based on this, if we actually look at Alice's contribution or Bob's contribution or Karen's contribution, it doesn't really make sense to the server. But when all of them come together, the antiparticles cancel out, and we only have the actual model going into the server for training. So it's almost like a mask that you are, giving on top of someone, so that the model that they are trying to contribute stays private. So each contribution looks random on its own, but when all of them come together for aggregation, they cancel out and they give actual model for training. So, do we have any questions on how does this work? Right, cool. So this is pretty much similar to homomorphic encryption, right? We are masking the data. We are making it random in nature, such that the server doesn't understand. But at the end of the day, the server actually gives out an output that we are deciding for. So the difference between these two is, secure aggregation is fast, efficient, and scalable, whereas homomorphic encryption, as we already discussed, is computationally heavier and it's slower. In secure aggregation, it protects the input, but the output that you are getting is the actual output that you're aiming for. Whereas in homomorphic encryption, it protects all the intermediate steps as well as the output itself. As we already saw in the previous example, the output that we got itself was an encrypted value. And only by applying the key on top of it, we were able to get the decrypted value. So the secure aggregation limits only to aggregation functions. They only limit to functions which do summation, and but in homomorphic encryption, it can handle complex computations like multiplication, matrix multiplication, and all those stuff. So if suppose you are writing a federated algorithm, which is not just using aggregation functions, but it is also using complex computations, then you have to go for homomorphic encryption. And that's what IBM has also done. They have implemented a federated learning system with the homomorphic encryption layers, and they've also released a library called IBM Federated Learning Library, which people can also use open source. So we saw how homomorphic encryption ties up with the federated learning and how secure multi-party computation ties up with federated learning. Differential privacy also ties up with federated learning, which we already saw in the workflow diagram. So we'll see it in depth here. So this is local differential privacy, where this is global differential privacy, where the edge device actually sends out a model, an updated model. And then in there itself, in the edge device itself, we can clip the contribution of that particular model when it goes to the server. And the clipped values of that model is what gets aggregated on the server. And on top of that, we will, we'll add noise, and that will become our updated model. In local differential privacy, the noise won't get added in the server, rather it will get added in the edge device itself. The clipping process and the addition of noise process happens in the edge device itself, and only after doing that, that particular model goes into the server, and that's where the aggregation happens. So this is an example of how it happens. So the model goes to all the edge devices, and then the training data that's there in the model will train the model, and on top of that, we limit how much a particular model should contribute, and we'll add noise to it. And after that, all the models will get securely aggregated using secure aggregation. And then the model goes back to the server, and the server will update itself. And this process will go on and on again and again. So this is how it has, this is the performance metrics that we have got for differential privacy on federated learning. Here we can see the most important thing, which is it gives around 4.634 for 763K users, which is actually really good in number. when we saw it is going to be between 1 to 10, then it needs moderate privacy. And it also gets 1.152 when we are using it with 1 e to the power 8 users. It's like what, 10 million users, I think. So the climax is not going to be something like, this is how the federated learning is moving forward, or this is how these are all the disadvantages of federated learning, because it's an all evolving process that's happening again and again. There's like a lot of research that's going on, and there are like a lot of industries that are picking it up. But it's going to be like a simple story of mine and how federated learning impacted me as a person. So I was introduced to machine learning pretty early in college, but when I got introduced to federated learning, it made me think of how secure our data is. What are all the data that we are using? Are we even using the necessary data for this model? Can we actually cut out these unnecessary data? And all these questions started coming up once I started learning about federated learning and all these adjacent concepts related to federated learning, like homomorphic encryption and differential privacy. So what I hope this particular lecture would have given all of you is not learn some complex terms, but actually to think about data protection from design itself. Let it be for really simple use cases, or even for complex deep learning and machine learning use cases. I hope everyone takes this particular thing that is taken away from GDPR back home, which is to think about data protection by design. And that's all I have on this favorite topic. If there are any questions, I'll take it. This is the feedback QR code. Please share your feedbacks on the DevDay that was conducted. It's really important for us. So.